Here we have three examples, three binary operations defined on this set and given to us using what we call Cayley tables. Okay, these are something like multiplication tables, and um, usually we take the first element from the rows and the second element from the columns. Remember, the order is important, and this star operation is defined in this manner. Um, and the cross product operation is defined in this manner. For instance, C times D. So C is here, the first one, and D is here. So it gives you a D. Or if you look at here, A star with C. This is the first one. This is the second one. And this is the result. Makes C. Or for instance, this one, D dot with C. This is the first one. This is the first one. You get the result as D. Okay, this is how you read Cayley tables. You get the first element from the rows, the second from the columns, and where they match, you obtain the result. Okay, looking at the Cayley tables, we can make some definitions. First, we talk about identities. An element E of a set A is called a left identity if this holds. If this element, when multiplied from left by all other elements, well, I'm saying multiplied, well, because you see, I dropped the symbol altogether here in this notation, but multiplication here, remember, this is quite important, it's an abstract multiplication. It's not the multiplication we know of. It's just an operation, however it may be defined. Okay, so uh, when an element E, when multiplied from left with all the elements, if the result is E itself, sorry, this should be X. This should be X. And if this is satisfied, we call this a left identity. Okay, so for instance, take the star operation. C star A is A, C star A is A, C star B is B, C star C is C, C star D is D. Okay, I'm multiplying all these from left with C, but the result doesn't change. It's the element itself. Okay, so in a sense, this has no effect on the element. So that's what we call a left identity. We also have the corresponding right identities. Again, this should be X. So when you multiply all elements from right by E, the result should be the original element. You have to be careful here. We define a left identity and a right identity. These may not be the same, or these may not be unique. Of course, when you look at the Cayley table, you see A, B, C, D here, the same as the column headings, which denotes that C is a left identity. On the other hand, this operation, the star operation, it does not have a right identity. On the other hand, when you look at this operation, I see that C is still a left identity, but at the same time, C is also a right identity. Okay, when I multiply elements from right with C, the result doesn't change. It's still the element. Okay, this means with respect to this operation, C is both a left identity and a right identity. If that is the case, we call this element simply an identity. Okay, how about this one? C, as you see, is a left identity, and it's also a right identity also. Okay. Let E be an identity element, and when I say identity, you should understand this as both a left and a right identity. For all xy in the set A, if x times y equals E, we say that x is a left inverse of y and y is a right inverse of x. Again, the order matters here. And for instance, when you look at the star operation, we see that, let's take B and E. If you operate on them, B star A, you get A. But if you switch the order, you take A first, A star D, you get D. Okay, the result is different. So we are going to see this in a minute, which means star operation is not commutative. Okay, so the order here is important. Left inverse, right inverse, it matters. But of course, if an element X is both a left inverse and a right inverse of element Y, again, we simply say that it's an inverse of Y, just inverse. The notation of inverses depends on the context. If you denote your operation as an addition, for instance, it doesn't have to be an addition, but you are using this sign, then in that case, we usually use this notation to denote the inverse. If you are using a multiplicative notation like this one, or simply without any symbols in between, we usually use this notation to denote the inverse. For instance, A and D, B and C are inverses of each other with respect to this operation, which you can check from the Cayley table. And A, C, and D are inverses of each other with respect to this operation. And in this operation, B has no inverse because no element satisfies the definition here for B. Another definition is for the absorbing element, or sometimes we call this an annihilating element or a zero element. An element Z is called an absorbing element if for all x in the set, x times Z equals Z times x equals Z. So which element you operate along with this element, the result is always going to be Z. Okay, this is what we call an absorbing element. Again, similar to inverses, left and right absorbing elements can be defined. I'm leaving out all the definitions here. And as I said, we can call this an annihilating element or simply a zero. Now, in this operation, you see B is both a left zero and also a right zero, because whatever element you multiply with B, the result you get is B. Okay, this is what we call a zero. In the other two, we do not have any zeros. Okay, so finally we are defining the commutative property. Of course, a binary operation is commutative if for all xy in the set A, xy equals yx. That means the order you apply the operation doesn't matter. If you get the same result, we call the operation commutative. Of course, as we have discussed just now, star operation is not commutative. B star A and A star B are different, for instance. Therefore, star operation is not commutative. You can also see this from this table. If you view this as a matrix, it's not symmetric. Okay, for an operation to be commutative, of course, its Cayley table should be symmetric, like this one. When you look at this, this is symmetric, this table is symmetric, therefore, this operation is commutative. I believe so is this one. Okay, so these two are commutative, but the star operation is not commutative. And a binary operation is said to be associative if this is satisfied. For all x, y, z in set A, x times y times z, so you apply the operation to this pair first, and you get some result, and you get some other result when you apply the operation to this first and after that to Z. If the two results match, we say this operation is associative. Okay, this is a very essential property of binary operations, and almost all of the algebraic structures we are going to define are going to be dependent on associative operations. From these three operations in this example, the cross is associative, this one. We would like to check that for all possible triplets, A, B, C, A, B, D, B, C, D, and you have to also switch the order C, A, D, B, A, D, D, B, C, etc. All of those possible pairs, you need to check that this holds. But if you do, you will see that this is associative. On the other hand, the star operation and the dot operation here are not associative, and you are given some counter examples here. There are also others.